I'm going to give a talk from Lightwave Logic on advancing integrated photonics with electro-optic polymer modulators. So for the next 20-25 minutes, I'll go through a bunch of slides, and I'll have to remember to time myself. So we're a public company, so I have to put this slide up, which is a safe harbor slide. Just a quick slide to say who we are. We were actually uplisted. That's a financial term to the NASDAQ stock market last week, 1st of September. What is unusual is when companies uplist, they usually have a reverse split or they raise money, but we actually were able to do this organically, which is extremely rare. But essentially, I don't expect anybody to be a financial expert here, but we don't have any debts, and the valuation is reasonably high. And the big takeaway from this slide is that it looks like, as Vladimir said in the past talk, that the valuations of photonic companies are actually beginning to go up again. And I haven't seen that for a long, long time. We saw that with Rockley a couple of weeks ago, and we're seeing the same sort of effect here, a market capitalization of over $1 billion. So this was on Friday. We were actually invited to close the stock market by ringing the bell on the 10th of September. And it's one of those occasions where it probably only happens once in a lifetime. And it's probably the only occasion you'll see me not wearing a black shirt. So I think this is the first time I've worn a white shirt in years. And you can see here, your picture gets on Times Square, so it's on the big board, as it were. And then as you get to the actual bell ringing, this is what it looks like. It's incredible energy, and you're carried on 4 TV stations live, so like Fox News and CNBC, so it's quite an interesting experience. And the person to the left is Jim Marcelli. He's the president and COO of the company, so we did the bell ringing together. So anyway, closing the market, and then I jumped on a plane to come to Europe. So let's talk about the real stuff here. We do electro-optic polymers. So you can think of that a bit like liquid crystal. You apply a voltage across the polymer and you can switch light very, very quickly. And that's really one of the key assets of this technology, and it can be done at very low power too. The current applications are clearly in telecommunications and data communications, because those are areas where you need to send traffic quickly. But if you think about this for a second, there are many other applications where you would like to switch light very, very fast. And so you can think of LiDAR, automotive, sensing, displays. And so, for example, in LiDAR, it's not only sending optical signals and getting those reflections and doing time of flight. What folks are actually concerned about is contamination. If all the vehicles have LiDAR, how do you stop contamination from one LiDAR reaching a different car? So you have to encode the signals. Encoding the signals actually requires fast modulators. So you're seeing some other opportunities crop up now, which are pretty exciting. Now, Vladimir may disagree with some of these numbers, but these are numbers that are estimates of different market research organizations that look out a decade. So there's a huge error bar here, so they're not expected to be accurate. But what I'm trying to convey is existing markets are clearly, for us, fiber communications, high-performance computing, DCI data center. But you can also see opportunities for integrated photonics emerging in a whole bunch of different market applications. And depending on who you look at in terms of a market forecast, or whether it goes out 3 years, 5 years, or 10 years, there's some big opportunities here. And so this is one of the exciting things we're seeing in integrated photonics in general today. So in terms of technologies, the previous speaker just talked about silicon photonics. I think the big news over the last 5 years is that silicon photonics is now an incumbent technology. It's matured. You've got the Ciscos and the Intels, and so a lot of the big foundries are using silicon photonics these days. So you have to include that with gallium arsenide and indiumphosphide. But what I've said in the bottom part of this slide is that there are new platforms not only polymers that we talk about, but there's dielectrics, there's glass, there's lithium niobate thin film, there's plasmonic designs, there's barium titanate. So what we are beginning to see is like a sea of new technologies to improve the incumbent technologies, whether you want to call them additive or not. But what we are seeing is you're seeing things like barium titanate and polymer used with silicon photonics. So you're seeing a mixing of the technologies. And what this really adds up to is, if this pointer works, is a term that we're beginning to use, at least over the last year, is hybrid PICs. They're not pure play anymore. So historically, we've had pure play gallium arsenide, we've had pure play indiumphosphide. We may see pure play gallium nitride, right? But the message here is we're seeing new technologies enhance different aspects of that integrated photonics platform. What Lightwave Logic is doing is working on the polymer side of it. And so this is a slide that I've taken from Yole. And it's a very interesting picture that shows you all your different technologies that are being worked on. And so towards a integrated photonics platform. And so, what combinations make sense for a hybrid PIC? It may be just polymers, it may be polymers plus something else. Or it may be two or three things that added to a base platform. That base platform could be indium phosphide, or it could be silicon photonics. So the challenge is to further pick performance with other materials. And that's where we see a really big opportunity, where I don't think you're going to see pure play integrated photonics platforms, but you're going to see a mixing and matching of the technologies. And so this is one way to look at this. If you look at the two big incumbents, on the left you've got indium phosphide, on the right you've got silicon photonics. You can see some of them have limited attributes. Well, we know we don't have a silicon laser, so we think of innovative ways of bringing the light on board, or we flip chip bump lasers on a silicon platform. So this is sort of where we are today, but these incumbent technologies really can't do everything. You can't do DSPs and ASICs in indium phosphide. That'd be very expensive on one hand. On the other one, silicon is having difficulty making the laser. And so the right thing to do is think about how you would improve that performance using other materials. So this is a very simple slide to show hybrid technologies make a lot of sense, and they certainly can boost that performance. So just talking about REO polymers. REO polymers are in three different platforms. You have the classic polymer stack modulator with a core and two claddings and just a trenched waveguide. So that's what we will call a three-layer stack. It actually generates very, very high performance. That's put on silicon substrates. In the center is what we call Polymer Plus, where you literally just add in the polymer to a silicon photonics platform. So if you've got a silicon photonics platform and you want a faster modulator, you can do that. And so you don't have to change anything else out. You just want to put faster modulators on your platform. And you can integrate that as a natural PDK with silicon foundries. And on the right-hand side, polymer slots have been around a long time. There's a lot of companies working on polymer slots, but as far as I know, they're not been commercialized as of yet. But it looks like there's been a lot of progress in the last 2 years towards very high performance polymer slots. And the big advantage of a slot is it's very, very small. So the footprint size is extremely small. So if you're thinking of using a very high speed modulator in a very small footprint, it could be a pluggable type scenario, or it could be onboard optics with a small form factor. That could actually make a lot of sense. And clearly you can integrate this. Well, the laser doesn't really work. But you can integrate this with PDKs or silicon foundries. And so there's some options here to really try and improve your technology. So we did one test of our polymers. This is just a basic test setup with a sampling oscilloscope and pattern generator. Now our pattern generator by Keysight can only go to 65 gigahertz. So that was the fastest that we could buy and the fastest we could set up at the time. And so I think I went past the slide here. So there's a slide missing, but I don't know where it went. Oh, there we go. So with this test setup, At slow speeds, obviously you can get nice square eyes, but the fastest you could go with a 65 gig amp using a standard stack modulator, electro-optic polymer modulator chip was reasonably clean eyes at 65 gigahertz. And we couldn't push it any faster because the system wouldn't go any faster. And so one of the things we had to resort to is just using vector network analyzers to get faster bandwidth measurements. And so when we did that, we started using PNAs, or programmable vector network analyzers. They're rated up to 110 gigs. You can see from the electrical S11 is pretty clean all the way up to 110 gigahertz. In sort of the reflection is below 10 dBs, which is really good to see. But on the right-hand side, you've got the electro-optic 3D bandwidth just short of about 110 gigahertz. And that's typically what we see from our modulators. And that's interesting because we're right at sort of the end point of the measuring system. And so after that, you have to sort of extrapolate to see how fast devices go. But if you've got devices working at 110 gigahertz bandwidth, that's typically 2 to 3 times faster than the natural bandwidth of devices we're using today. And so you have to think about how that's going to impact the traffic on the network and the power consumption that's required to do this. And so you can see some of the other technologies. I mean, we do hear about 50 gigabits per second, 50 gigabaud, 110 gigabaud, but if you translate all those data rates, whether it's PAM4 or NRZ, back to the natural 3 dB bandwidth, the 3 dB bandwidth, these optical devices are in the 30 to 40 gigahertz range. And if you look at hero papers by Indiumphosphide, I think I've seen some at 60 gigahertz. And so it's really interesting to see if you've got a technology that's got a natural high bandwidth, that gives you a lot of degrees of freedom on how you want to encode the signal. If you look at some of the comparative performances, these are just the spider charts. What I'm showing here is that polymers do cover in terms of these 4 quadrants, speed, size, low power, and stability. And from a silicon photonics standpoint, it can really actually have a big impact in your performance of your integrated photonics chip. In terms of technology strengths and weaknesses, and I've included lithium niobate and thin film lithium niobate, as well as barium titanate. I mean, there's a lot of different technologies with a lot of different attributes. This is the impact. This is your classic 3D graph that you see in a lot of different technical papers. And what we have here on the vertical axis is modulation with bits per sample. And we have gigabaud coming down here on the lateral axis. And in the depth, we have the number of lanes. And clearly, you'd like to have a single lane at very high speed. Everybody's been trying to solve that problem. And so what people have gone to, as you can see from these red spots, is that you go to 4 lanes, or you go to 8 lanes, or you go to PAM4 in order to try and get your data rate speeds up. But if you've got a naturally fast device, then you can actually go much, much faster. 100 gigahertz bandwidth is 150 gigabits per second. And you can see over here, 150 gigabits per second is 150 gigabaud NRZ in 1 lane. If you want a PAM4 that, you're going to 300. And if you want 4 lanes, you're over a terabit. And so faster devices is certainly going to be one of the ways you're going to solve and simplify your encoding techniques. And if you can implement that with a silicon photonics platform that's got existing muxes and demuxes, then I think you have a really interesting solution. So it's okay to put polymers down on a piece of silicon, but you've got to do it in a way that you can scale it and you can increase volume quickly. And so this is just a roadmap I show typically financial investors. So it's fairly high level. But what we focus on is what's unique about what we're doing, which is really the electro-optic polymers and how you design them for high speed in a modulator format. And so you have to have unique value to the industry. But on the lower right-hand corner, you've got to be able to integrate that with big silicon foundries. you've got to get into the PDKs, the process development kits. And so what is a process development kit? It's basically the process travel a big silicon CMOS foundries use to do all their steps. If polymers can be totally integrated into that format, then silicon foundries can offer electro-optic polymers as one of the assets, one of the benefits of a silicon photonics design. And so that is a great vehicle to get our technology onto large-scale wafers, 200, 300 millimeter, and scale it up in volume. So partnering with foundries is certainly the right direction for us. But what's interesting is since the maturity of silicon photonics over the last few years, I remember 5 years ago, and I remember 10 years ago, there was some silicon foundries that saying, well, we're not really interested in this silicon photonics because it doesn't have the volume. In telecommunications and data communications doesn't drive the volume. But you just look at companies like Rockley, they're getting into the medical space, they're getting into the automotive space. Now the silicon foundries are going, wow, this is a huge opportunity in volumes. It's not just data communications, optical communications, it's automotive, it's medical, it's bio, it's sensing. And so all these big foundries are actually showing a lot of interest to get into this space very, very quickly. And so this is driving the volume scale of silicon photonics. And if you can actually boost the performance, then I think you're on a winning platform. So the other thing to work with foundries is you better have really strong patents, because foundries will want to be able to license your technology or even technology transfer your technology. So in order to do that, you better protect yourself. And so for us, it's not just selling components or that as our main driver, but we better be in a position to work with the foundries and license or tech transfer our technology of EO polymers. And so trying to increase the patent portfolio quickly takes time, because as you file a patent, it takes a year to 2 years to progress through the patent procedure. But in the meantime, we acquired some of the older patents from Lumiere and Gig Optics, which were doing electro-optic polymers 5-10 years ago. So we've built our portfolio in terms of making sure you can design electro-optic polymers with silicon photonics so you have a good position moving forward. And the last couple of slides are more generic, but because I've been involved in a lot of the integrated photonics roadmaps, I always get asked to show a few roadmap slides. So I don't think I'm a Nostradamus or anything like that, but I think it's good to see over the next 10 years where the technology is going. And I think one of the things I have to do is actually put down gallium nitride, because Christoph here is going to talk to us in the next hour about gallium nitride, and that's a new technology that I didn't even list until today. So next time I'll have that listed. But what these roadmaps are about are product vehicles at the top, and the years, you can see the years go up to 2028. And then you've got down here on the bottom left, the technology platforms to get there. So you can see there's Indiumphosphide, there's silicon photonics. So simple metrics. And the rest is blanked out because I got that on the next slide. And so in black font is what you'd see from normal R&D funded, either by governments or by commercial industry. And then that's on the left-hand side. On the right-hand side, what's in red font is where you really need to invest to get there. So whether you invested or the government invests, but the money isn't there to get there yet. But it's clearly that is the direction to go. And then in the middle is what we call the purple brick wall, which is the technology barriers. And I put in there cost barriers, because in photonics, we may be able to solve a solution, but it may be this big, or we use an optical lab to do it, or an optical bench. But it's got to meet the cost performance in order to be practical. So, everybody's talked about optical computing, but, optical computing is still the size of a lab. It's not the size of, a silicon DSP microprocessor chip or a GPU or anything like that. So a technology cost barrier. And basically, there's going to be a lot of information. So you can find this presentation on our website. So you can download and see the details if you want to go into the details. Certainly, you're not going to see it from sitting back there. But you can see there's a trend. You can see where those purple brick walls are. You can see areas where it's really tough to design things like, a 1600 gigabits per second transceiver is not going to be easy to design. We're talking about 800 today. There's some ideas how to go to 1600. What do you do after that? I mean, what sort of level of integration do you need to do that? I mean, that's really tough to do. How do you design really faster devices is not easy. And yet, some technologies can actually go quite quick, and so you see that trend. And so, yeah, I would encourage you to look at the details because it gives you some idea of what's going to happen next. And then the last couple of slides is nobody's really done this before, and I think this is a first. And this is a draft packaging roadmap, because if you think about integrated photonics, whether you package it, whether it's chip scale for onboard optics, or it's chip scale to go into a pluggable vehicle of some kind, or you don't have any vehicle at all, or you just still want to put it in a gold box or a plastic globe top or something, I think we as an industry need to see where this is going. So this is still in draft form, probably going to be updated. And what I'm doing is I'm trying to work with a lot of people, especially the EPIC group and a few other folks, to try and get a lot of input into trying to see where packaging is going over the next decade, because you can't just design a chip, at least working at 100 gigahertz, without understanding how you're going to package it. I mean, the two things are actually going to have to be related, because you're really designing a microwave type chip. And we've seen that from the gallium arsenide MMIC business over the last 10, 15 years. So a packaging roadmap. So to summarize, what we're about is a technology platform to actually send traffic faster at lower power using really high-speed modulators that switch light quickly. Our devices now are over 100 gigahertz bandwidth, which gives us a lot of degrees of freedom. They're working at a volt or less, so that's pretty exciting. If you think about this for a second, it's not really the cost of the component. If you can work at a volt or less, then your modulator can be directly driven from your DSP or ASIC chip, so you don't really need a driver anymore. And so you're saving the customer money in terms of IC. So that is something to think about. We make our own chromophores and polymers in-house in Denver. And we work with multiple foundries and different partners so that we can leverage ourselves. We're not going to get into the module business per se, because there's 20 companies to do that. But there's not many companies that can do electro-optic polymers. And then lastly, technology roadmaps guide us, and packaging is next. And feel free to email us if you have any questions, or catch me. I'm going to be at the conference this week. Thank you.